The worksheet has questions on it that are similar to some that we've done before and also similar to your homework. Does anybody want a copy of the worksheet? Yep. Thought I brought them in here. You said there?
Oh, I already have it on the computer. Thank you.
Okay, so the first one says, we have, I know you can't see that there, let's see if it's, we need to turn out the lights. Okay, so for this one, we're supposed to make a 4-bit synchronous counter with parallel load and a minimum number of additional gates that counts from 0, 1, 1, 0 to 1, 0, 0 inclusive, and then wraps to 0, 1, 0, 0. So 0, 1, 1, 0, and it's going to 1, 0, 1, 1. So it needs to go through all of those stages and then go back to 0, 1, 1, 0. So that's how we want our counter to work. And so the way you do that is you attach a high voltage to the enable, and in digital logic we just call that a 1. And this is the most significant bit, that's D3, and then D2, D1, and D0. So D0 is 0, D1 is 1, D2 is 1, and D3 is 0. So just be careful with that because it's a palindrome. It looks the same forward and backwards, but if you have a different one, remember the order that you read these, it's like goes in this order. And we'll put the clock here. And the output that you get here is going to be the count. So the first thing that you're going to get would be 0, 1, 1, 0. And then the second thing you would get out of this, so that'd be the first thing you would get. And then the next thing you would get would be, so this would be the 0, 1, 1, 0, and then the next thing you would get would be 0, 1, 1, 1, because this is Q3, because that's the highest order bit, and then the next one you would get would be 1, 0, 0, 0, and then 1, 0, 0, 1, and then 1, 0, 1, 0, and then we want it to stop when it gets to 1, 0, 1, 1. So if we look at these bits that I did not draw very smoothly, let me try this one more time. Okay, so that's just showing the order that they would come out. And then we want it to stop when it gets to that 1101 right there. And if you look at all of the instances that come before that, the only one that has a 1 in Q3, Q1, and Q0 is the last one. So if I take Q3, Q1, and Q0 together and AND them together and feed that into the load, what that's going to say is load when you get a 1 in each of these spots, because that's the only time that this AND is going to be 1. And no other time before that is that AND going to be 1. So then it'll load, and then you'll go back to 0, 1, 1, 0. Question?
Yeah, so we want to make a clock that goes from this number to this number, like that counts from this number to this number.
Right.
And we're doing those numbers in binary. So that numbers to the right are those numbers. So for example, I think it's like a 70 or something.
So this one starts with 6, 7, 8, 9, 10, 11, 12, and you go back to 6, 7, 8, 9, 10, 11, 12, or 13.
Right. So
Yeah.
we're going to make a clock that comes from like 6 to 13.
Mm-hmm.
So that's like, or those are like a range. But what is our Q0 to Q3? What are like, where are
Those are the outputs of the counter. So that's the actual number that it's outputting. And so it's going to output it in binary. And so it outputs the number, so it's outputting this number, where this is Q0, Q1, Q2, and Q3. And so right here, the first number it outputs is that one. And then on the next clock cycle, Q3 is 0, Q2 is 1, Q1 is 1, and, or sorry, it's this one. Okay, so the clock is counting, what did I say it started with, 6? 6, 7, 8, 9, 10, 11, 12, 13. But it counts in binary, so it counts 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1. Well, how are we going to get those numbers? Those numbers are going to be on wires, and this wire is Q3, this is Q2, Q1, and Q0. So I don't know how it's lined up, Q3 at the bottom. So it's lined up with Q3 at the bottom, and then Q2, and then Q1, and then Q0. So when the output is supposed to be 9, then you would get a 1 here, a 0 here, a 0 here, and a 1 here.
Oh, okay. Okay.
And then on the next clock cycle, when you get 10, you would have a 1, 0, 1, 0.
Okay.
And so we are trying to detect when it gets to the number 13, which is this number, and we can detect that by finding out, well, when are these 3 wires equal to 1?
Is it 13 or 11?
Was it 11?
I think it,
Did I? 8, it's 11. It's 11, yep. So I counted too far. Yeah. It's 11, which I meant not that. 1, 0, 1, 1.
So
Yeah,
on
just
the,
11.
On the left, we have our initial number, which is 6, as D0, D1, D2.
That's what we load.
And on the right, we got routing, which is from 7 to 11.
Well, 6 to 11, right?
6 to 11. And so it's like this environment, right?
Right?
And we want to find environment, which is the number one account.
We want to detect the number that we need it to stop at.
And that's like the number where when the average where 11 is 1.
Yes. So if I wanted to count from 4 to actually 13, well, let's do 4 to 14. So 4 is 0, 1, 0, 0, and 14 is 1, 1, 1, 0. Then I would have 0, 0, 1, 0, and Q0, Q1, Q2, Q3. I would AND together Q1, Q2, and Q3. Because that's where those are all ones. Okay, but you can be tricky, and let's say oh no, I'm not being tricky. I'm not being tricky. I could be tricky and say, instead of doing the one that I had on there, count from 1, 1, 0, 0 to 0, 0, 1, 1. So we're wrapping around, so that would be counting for 12, 13, 14, 15, 0, 1, 2, 3. So in that case, we have to be a little more careful. So we know that Q0 and Q1 have to be 1s, but that's not going to be good enough because that is also going to happen at 15. So I would want to include on this one that these two were 0. And that would make sure that I was safe. Okay, so you see how you would do this one now. It says from 0, 1, 1, 1 to 1, 1, 1, 0, 0 inclusive. Same idea. Okay, so now let's look at a Johnson counter. For a 4-bit Johnson counter, starting with the sequence 0, 0, 0, 1, list the sequence of states after each clock until the sequence repeats. How long is the sequence? Do y'all remember how the Johnson counter worked? So what happens is the last bit flips and goes to the front, and the other 3 bits slide down. So this would be, if this is your first one, this is going to be your second one. So the last bit flips and moves to the front, and the other 3 bits slide down. So this will flip and go to the front, and then the other 3 bits slide down. So what would the next one be?
1, 1, 1, 1, 0.
1, 1, 0. Uh-huh. And then the next one,
1,
uh-huh. And the next one,
that'd be 0, 1, 1,
and you tell me what's the next one going to be.
Is it 1011?
No, so this one changes and moves to the front,
Oh,
and then these three slide back.
okay.
Okay, so now tell me what's the next one going to be.
So it's gonna be 0, and then the last two, which is 0, 1, 1.
Right, which was where we started. And so let's see how many states that was. 1, 2, 3, 4, 5, 6, 7, 8, which is not a coincidence. So how long is the sequence? It was 8. So for an n-bit counter starting at 1, 0, 0, dot, 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 0, 0, so we have n bits in here altogether. How many do you think it would be before we get back to 1, 0, 0, 0, 0, dot, 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 0?
N states?
It's actually going to be 2n.
Or 2,
Yeah, because if we think about what's happening, the last bit's going to come around to the front, and we're going to do that until we get all ones, and that's going to happen n times. And then we'll have another n times to get all the zeros back. Because if you just do it, the way to do things like this is just to try it out. Try it with a 2-bit. So 2-bit, you would have 1, 1 would be your first one, and then 0, 1, and then 1, 0. Let's see, 1, 0, 1, 1. Oops. 0, 1. Nope, 0, 0, and then 1, 0. So that would give us 4. And then try it with 3 bits. So if I had 1, 0, 0, I'd get 1, 1, 0, and 1, 1, 1, and then 0, 1, 1, and then 0, 0, 1, and then 0, 0, 0, and then 1, 0, 0. And you can see that with 3 bits, I got 6 states.
We don't include the final state, like the one when it goes like that.
No, because it's identical to the first one. Hold on. There's no one in the Zoom, right? I can get off. Okay, all right. All right, so now, yeah. Okay, so that was that one. All right. Now we're supposed to write the Verilog for this. So this is just a multiplexer. So module question 3 with inputs P, Q, S0, S1. And my output F. Okay, so okay, so then we'd have input P, Q, S0, S1, output F, and then we can say case S1 comma S0, and so what that does is that puts S1 and S0 together and makes a 2-bit number out of them. And we could have two B00 colon 2B01 colon 2B10 and 2B11. And so if S1, S0 is 0, then this should be output, we need to make that a reg, and I think you put the reg before the output. I always mess that up. And I don't have it here. I can't ever remember if you put the reg before the output or
I think it's output reg.
output reg.
Mhm.
The reason we have to make it a reg is because, oh no, we don't have to make it a reg. It's not in an always block. Never mind. It's not in an always block, so it doesn't need to be reg. So we would do assign F equal to P exclusive OR Q, and that's the Verilog for an exclusive OR. And here we would assign F equal to not P and Q. And we would assign F equal to P. And we would assign F equal to not P and Q. I can't draw an and. That's supposed to be an and. And Q. And then end case and end module.
Is not P and Q for both the second and the last one?
Now, the last one is not P
Oh, I
and
see.
Q, and then the second one is the NAND. So it's P and Q, and then you not it.
So those like what is like next to the center left are binary numbers, and those are the binary numbers that are like 0, 1, 2, 3.
Yep, yep. And that's what's going into each one of them.
Oh, and then we just throw them in like the gates.
What's that?
And then like the E not Q is just like the gates that are like going to each number.
Yep, so 0 is the exclusive OR of Q and P, so that's where I have it here. Okay, so when I see something like this, and I see parameter n equals 4, I see always at positive edge of a clock, they're telling me it's a sequential Verilog. Q goes from 3 to 0 because n is 4. I know that this is going to be something that has 4 D flip-flops. And I'll call this one 3, 2, 1, and 0. And they'll each have the clock. And this for loop is going to tell me what is going to happen to each one of them, like what the input is going to be. If I had an if statement in there, an if statement would tell me I'd have a multiplexer going with each one. And usually you do have that, but here there is no if statement, so we don't have a multiplexer. So a multiplexer would be used if we had an if statement, but we don't. So this is saying starting from 3, as long as we are greater than 0, so from 3, 2, and 1, we're going to go through this for loop. And the first time we go through, k is 3, and we're going to say that Q3 becomes equal to Q2 because k is 3. So this is saying Q3 becomes equal to Q2. And this operator here makes it so that it doesn't actually change the values of the register until you get out of the always block, so you don't have to worry about accidentally writing over something that you need to use. So Q3 becomes equal to Q1. So this, here's Q. Q is the output. Q3 becomes equal to Q2. So Q2 is the input to Q3. This for loop is only one line long, and so we'll go to the next one. Q2 becomes equal to Q1. And then Q1 becomes equal to Q0. And then we're out of the for loop. And then it says Q0 becomes equal to the naught of Q3 exclusive OR A. Okay, so I have Q3 exclusive OR some variable A, and that is my value for Q0. And then I assign y equal to Q1. Don't know why I'm doing that, but I can. So just, that's why. So if you see one of these on the test, you can be pretty sure you're going to have D flip-flops. I'm pretty sure that you'll have the clock. The only thing that might be different would be if you had an if inside there. So if I had like if R QK becomes equal to QK minus 1, else QK becomes equal to QK. Then in that instance, what you would have, like let's say I had here flip-flops 3 and 2, and here's my D, and here's my Q, here's my D, here's my Q. You'd have a multiplexer going with each one. And the input to your multiplexer is going to be what this if is. And the output of the multiplexer is going to be what goes into D. And then it says if R, that's the same as saying if R equals 1, QK becomes equal to QK minus 1. So this is if it's 1, so we're going to use the 1, and that would be Q2 going to Q3. And the one from Q2 would be going back to the one that's Q1 over there. And then the else would go with Q0. The else says, else it feeds back into itself. And that goes into the 0. So that's if you have an if statement on there. And so, but, all right. And then the last one. For a 5-bit ring counter starting from 00100, list the state after each shift until the sequence repeats. So how is a ring counter different from a Johnson counter? Does the same thing, but it doesn't flip. So the one at the end just goes to the beginning. So we can see that it took 5 states, which makes sense because you're just taking the one from the end and putting it at the beginning. And so the maximum you would ever have to go through is however many bits you had. Now, we might get there quicker with this one. What would the next state be for this one?
0, 1. Oh wait. Sorry. 0, 1. 0, 1, 0.
Mm-hmm. And what would the next one be?
0, 0. 1, 0, 1.
Yeah, so this is a ring counter, so you don't flip it. Okay, and then what would the next one be?
1, 0, 0, 1, 0.
And that's not back where we started. Okay, and then
And 0. 0, 0, 1. 0, 1, 0.
yep. And so it did in fact take 5. Actually, I think, yeah, I don't know. I don't know if there's a pattern for that.
So if they give us and so the state is going to take is the number of bits
For a ring counter.
for a ring.
Well, the maximum it could be is the number of bits. It might be less. Like, let's say I had 1010. What would the next one be?
1 1 0.
0 1
Oh, for the
0.
ring one.
Yeah, for the ring. And then what would the next one be?
It'll be 1 0 1 0.
Yeah, so this one it only took 2, not 4. So it just depends. So, but the maximum it could be is n. And for a Johnson counter, the maximum it could be is 2n.
2 not like into the whole thing.
Yeah, right. So a ring, the max would be n, and Johnson 2n. And this is basically because for a ring, you have to basically like shift all the way through each bit. For Johnson, since you're flipping a bit, you have to do it twice to get them all back to where they were. Okay, other questions?
So in the homework they give us when we're doing like a circuit from a code they give us.
Mm-hmm.
They use like if qk plus 1. I don't understand like what the k or the k plus 1 means.
So you've had computer science, right?
It's not.
Yeah. So it's like it's a for loop. So it's just a number. So it's so if we look at you look at your for loop. Oops, that's a grade school. Don't want that. So n is 4. So what you would do with something, let me do not this one, but one that's like it. Let's see, would this have an if in it? It did have an if in it. Okay, so let me get one. Okay, so I just changed it so that we're not doing exactly the same thing. So I changed it so this line says Q of K becomes equal to Q of K and C. And this one says that's the if, and this one has the else. Q of K becomes equal to Q of K plus 1. I just put a not in front of it just to make it even more different. Okay, all right. So now it says our parameter n equals 3. So you can go through everywhere where you have an n and replace that with a 3. So then this line is reg 2:0. Our for loop is going to be for k equals 0, k less than 2, k equals k plus 1. So this first part here, q reg 20, what that tells me is I have a q2, a q1, and a q0. That tells me my circuit is going to have 3 flip-flops. I'll have 2, 1, and 0. Okay, then what my for loop is telling me is it's telling me that starting with 0, as long as I'm less than 2 and count up by 1. So this is going to go, I'm going to go from 0 and then 1, and then when I get to 2, I'm done. So yours is obviously going to go 0, 1, 2, because yours is going to be 3. And so the first time through my loop, k equals 0. So the first time through my loop, I have if E Q0 becomes equal to Q0 and C, else Q0 becomes equal to not Q1. So that's my first time through the loop. Okay, so Q0 becomes equal to Q0 and C. That's if. I have an if, so that means I'm going to put a multiplexer. And E is going to be my value into my multiplexer, and the multiplexer goes into 0, because that's the way the if statement works. And I have a 0 and a 1. If E, that's going to be the 1 value, then it equals Q0 and C. So here's Q0, and I'll AND that with some variable C, and that goes into the 1 of my multiplexer because it said if E. The else is going to go into the 0 port, so else it equals not Q1. So Q1 is here, and I can take the not of it and put that into Q0. So now I've done the for loop once. Next time through my for loop, k equals 1. So now my for loop looks like this. If E Q1 becomes equal to Q1 and C, else Q1 becomes equal to not Q2. I have an if, so I put a multiplexer. 0, 1. It's if E, so E is my input to my multiplexer. If it's 1, then it equals Q1 and C. So I'm going to take the and of Q1. This is Q1. Here's my C. I'll take the and of those, and that goes into my 1. Else it equals the not of Q2. So here's Q2, and I want the not of it to go into the 0. Then I'm out of the for loop. N was 3, so this is Q2. Q2 becomes equal to D. This was supposed to be a 2. Q2 becomes equal to D. There's no if, just goes right into it. And then it says assign G equal to Q0. So that would be G. And it doesn't look like we're doing anything with Q2 in this one, yeah. So that's what the K is.
Okay, so the K basically sort K is over flip-flop, right?
You're iterating through this for loop. It's going to take on this value first. So you plug that in for K first. And you keep going until you meet this condition.
Right. So, okay. Okay. So if we have 4 gates, it will be 0, 1, 2, 3. Yeah.
So if yours, yeah, 0, 1, 2, 0, 1, 2. Because yours starts at 0 and K less than, N was 4, 4 minus 1 is 3, less than 3, that's 0, 1, and 2. So you will have one more time through the for loop.
So you have to go through the entire sequence of how the loop would work in order to draw the circuit properly?
Yes.
That's basic, okay.
Yes. So let's see, what time is it? 4 o'clock. Okay, so take a look at this one. Let's take this. Let's change this to parameter n equals 5. Okay, so we see that we've got this Q in here. We've got positive edge of a clock. We know we're going to have flip-flops. N is 5. This says reg 40Q. So I'm going to have flip-flops. This is how you'll know how many flip-flops you have. We'll have 0, 1, 2, 3, 4. You have a for loop that starts at 0 and it goes until, so it starts at j equals 0, it goes until as long as j is less than 3 and j equals j plus 1. So what this means is we will have j equals 0, j equals 1, and j equals 2 that we'll do this for loop for. So 0, 1, and 2, we're going to do this for it. It's got an if, so each one of these is going to have a multiplexer, and y is going to be the input to the multiplexer because it says if y, and then you'd go through and do those. Yeah.
One question is, wouldn't j be j is 4 because it's n minus 1 and n is 5?
Yes, you're right. Yep. So then we'd have j equals 3. Yep. All right. All right. And I think that'll be it for today.